Alright, so this next example is going to work with the solution space of a given matrix, and what we're going to do is find its dimension. So here's the example. Find the dimension of the solution space of this matrix. So here's the matrix. It's going to be, it's going to be a 4 by 6 matrix, and here are the entries. So 1, 3, -2, 0, 2, 0. So that's the first row. The next row is going to be 2, 6, -5, -2, 4, and -3. So that's our second row. And the third row will be 0, 0, 5, 10, 0, 15. And then our last row is going to be 2, 6, 0, 8, 4, 18. So that's a 4 by 6 matrix. So the solution space is actually going to be a subspace of our N. So let's start the solution down here. So let's make that, write down what I just said. So by definition, W, I actually didn't particularly or explicitly mention that that solution space should be called W, so I'm just going to snake that in here just to insist that this example is simultaneously telling you that W is going to represent the solution space of this matrix A, and that we want to find its dimension. So that's why I can conclude now, by definition, W, I'm just going to copy this as this format and just figure out what it will be in this specific case. So in this case, A is 4 by 6, so my N in this case is 6, right? So remember, your N comes from the number of columns of your matrix. So this W is the space of all vectors X in R6, such that if you multiply them on the left, you get the 0 vector. And then in this case, this is going to be the 4-dimensional 0 vector. So just to be clear, this is the 0 vector in R4. So what we can say now, we can clarify this a little bit further. Let me write it down in the following way. It follows that if I write down a vector with 6 coordinates, I'm going to label them very specifically right now as x1, x2, x3, x4, and x5, and x6. Good thing I didn't cap that off. It didn't end up being long enough. So a vector with 6 coordinates, which I'll call x, is in W if and only if, well, if and only if I multiply it on the left by the matrix A, I get the 4-dimensional 0 vector. So let's spell that out a little bit. So I'm going to slide this up, and so I can actually continue on. So what that's actually going to look like if you spell it out is if I write a copy of the matrix A, which I'm going to try to do as few times as possible because this is a bit time consuming, but I also don't want to sacrifice clarity between my steps, so I'm going to write this out a few times as necessary. I want to have this all laid out in front of us. So this is just a copy of the matrix A. And the last row is 2, 6, 0, 8, 4, 18. And now I'm going to multiply it by x, by the vector x on the right. So we've got x1, x2, x3, x4, x5, x6. So really what I'm doing is I've now written out the left-hand side of this equation, but I've actually written out the entries of A, and I've written out the coordinates of the vector x, and on the right-hand side we're going to get the 4-dimensional 0 vector. Okay, so in other words, this 6-dimensional vector x is in, as I've written it out in general coordinates, is in W if and only if this equation is true. So what does that mean? Equivalently, we can consider the following. We can consider the augmented matrix of this matrix equation. Right? Remember, AM just is an abbreviation for augmented matrix. Let me slide this up a bit further. So what is the augmented matrix of this system? Well, you would just write it without the variables. Right? You'd write this out as the coefficient matrix, then you'd write a vertical line, and then you'd write your constant column. So this is the last time I'm going to write this out, but we do need to write it out one more time. So that's the first row. The second row, 2, 6, -5, -2, 4, and -3. And then the last row, 0, 0, 5, 10, 0, 15. And then our last row again, 2, 6, 0, 8, 4, 18. I'm going to draw my vertical line, and then I'm going to write my constant column. And the point I want to make is that these are actually equivalent. One just happens to write down the variables, right? So this is just another way of phrasing this matrix equation. As long as the variables x1 through x6 are understood, those are understood to be the labels for your variables. So really, if we want to figure out, let me slide this down just a little bit, if we want to figure out what the elements of this solution space W are, we really just need to find all the solutions to this augmented matrix. So we need to solve this, in other words. So what you need to do next is to row reduce it and carry it into Gauss, or use Gauss-Jordan elimination to carry it into reduced row echelon form. So I'm actually going to just tell you what that is. So what I'd encourage you to do really is to pause this video, as I sometimes ask you to do. Pause this video and take it as a personal task to row reduce this. And then when you resume the video, you'll see me write down the reduced row echelon form of this matrix, and you should have the same thing. So I encourage you to do that. But in the meantime, I'm going to go ahead and write out the reduced row echelon form. So I'm going to draw an arrow and say exercise row reduce. So I'll leave that to you to work out the details. But here's what you're going to get. For the first row, you're going to get 1, 3, 0, 4, 2, 0, and a 0 on the right-hand side. For the second row, you're going to get 0, 0, 1, 2, 0, 0, and then a 0 on the right-hand side again. Then for the third row, you get a lot of zeros, and then a 0 there, and then the last row consists entirely of zeros. So that's what it looks like if you row reduce it down to reduced row echelon form. And the reason you want to do that is because you actually want to write down explicitly what the solution set is to this matrix equation. And by this matrix equation, I mean this one up here. This is what we're trying to solve. And this is the reduced row echelon form of the augmented matrix. So now we're ready to write down the solution. I'm going to stop this clip and we'll